1/2 to the n. So do you all agree that that right there would be sum n equals 1 to infinity of 1/2 to the nth power? Yeah? All right? Okay. Yeah, no questions on that? Start plugging in 1, get this, 2, this, 3, this, 4, this, 5, right? Okay, I'm telling you this is a geometric series. Now, in this class, when we look at geometric series, in order for us to start working with them and doing what we need to do, we need them to look a certain way, all right? So I'm going to now show you the general formula for a geometric series. In general, okay, a geometric series looks like this. Sum n equals 1 to infinity a times r raised to the n minus 1. This was just to motivate the idea. I'm going to get back to this, okay? I'm going to get back to this, but now I'm just, oh, that one underneath there. So just, you can leave it, but it rolled over there. I'm going to leave that. Let's look at this. This is the general form of a geometric series. Let's write out the first few of these terms. So I'd like for you to plug in n equals 1. If I put 1 here, 1 minus 1 is 0. Okay, r to the 0 is 1, and then times a, right? So I get a first, plus, now let n be 2. So if I let n be 2, we get 2 minus 1, that's 1, r to the first power times a. So ar, a times r. And then what would the next one be? ar squared, ar cubed, ar to the 4th power, and that keeps going, right? That is what a generic geometric series looks like. They all have some number, a, that's in every term, and then they have some number being raised to a power that keeps going up. That's kind of what we had here, right? We had a half to the first power, we had a half squared, we have a half to the 3rd, right, like that? I mean, if anything, we do hopefully see that you do have a number in front of all these, right? There's a 1 in front of all of these. 1, 1, 1. So that's kind of like the a, 1, 1, 1. And the powers here come up. Do you see the powers here come up? Right? The one difference is that this one starts with the first power here, right? But do you see we're kind of missing this piece? But there's a big similarity between these two. Do you all see the similarities? Yeah? All right, so the question is, does this series converge or does it diverge? That's the question, right? We don't know. Well, I'm here to give you the answer. I'm just going to tell you the answer first. Then we're going to use the answer to answer this question. And then, if y'all want, I will prove why it is what it is. All right? So this right here, this series, will do one of two things. It will diverge if the absolute value of r is greater than or equal to 1. So if the number that keeps being raised to powers that get bigger and bigger, if that number that you're looking at, when you take its absolute value, if the absolute value of that number is bigger than or equal to 1, we have guaranteed divergence. Now, is our number that's being raised to bigger and bigger power, is that number r that we have, is it bigger than 1? The absolute value? No, right? So it's not that case for us, right? So what does it do? Well, here's what it does. It converges. Okay, if the absolute value of r is less than 1. Not only does it converge, I can tell you what it converges to. It converges to a divided by 1 minus r. What I'm telling you is this. If you have a geometric series that looks like this, all you have to do is investigate what r is. Once you know what r is, you can just check, is the absolute value of r greater than or equal to 1 or less than 1? If it's less than 1, it will converge, and it will always converge to a over 1 minus r. If the absolute value of r is greater than or equal to 1, it will diverge, guaranteed. All right? So you're probably sitting there maybe asking, like, why, right? Like, where does this come from, right? I can prove that to you, but let's do this problem first, all right? Let's do this problem first. So for now, we're taking this on faith, yes? Let's go look at our geometric series over here. We have this, right? And I want to know, does this converge or diverge? Converge or diverge? So what would the first thing you do be? Probably. No, I'm saying in terms of what we've learned here today. Nth term test, right? The nth term test. So you try your nth term. Nth term. All right, we're going to take the limit as n goes to infinity, right, of 1/2 to the n, right? That's our formula. Do y'all remember this from last class? You have a number to the n power, and that number is smaller than 1. What happens when you raise a small number to bigger and bigger powers? It goes to 0, right? So this goes to 0, right? So this goes to 0, right? Which means this test is inconclusive. Right? Inconclusive test. If it goes to something other than 0, then we could say it diverges. But it goes to 0, which tells us absolutely nothing. This is that failed pregnancy test, right? That's what that is. That's what just happened. So now we need to move on to the next thing, right? And we look at it and we go, wait a minute, hold on. This looks geometric, right? Doesn't it look like this, kind of? Kind of it does, right? Do we see a number in front over here on this formula? I mean, you could say there's a 1 here, right? What's the big difference in the formulas? That's an n minus 1, and in our formula, it's just n, right? That's what makes these two things different. Do y'all see that? Yeah. So I'm going to do something. You may or may not like this. I want to keep this on the board. I'm going to make that look like this. And I'm going to do something that we did kind of, you could say I kind of did this when we were learning about, do you remember there was a type of integral where I said, a type of integration where I said, I do it my way in the tutoring lab. If you go to tutor, they're going to do it their way, and you pick which way. Part of the reason why I showed you my way was because I'm going to do this using a similar technique. I'm going to make this an n minus 1. It's a hidden 0. That's what I'm doing. I'm make that an n minus 1. So I'm going to rewrite the original series over here, right? I'm going to rewrite that as sum n equals 1 to infinity of 1/2, and then I'm going to put, that's the original problem. I'm going to make a minus 1 appear by doing minus 1 plus 1. I'm allowed to do that, right? My goal is to make it look like this. So let me just continue. Sum n equals 1 to infinity. This is the same as 1/2 to the n minus 1 times 1/2 to the first power. This you have to just see. Right? If you have the same base multiplied together, two different powers, you would add those powers together, right? So that would be n minus 1 plus 1, which is what this came from. So basically what I did was right after the n minus 1, I split it and I broke it off into two pieces. Is that still the same expression? Yes. I mean, I haven't changed anything, right? I mean, it looks different, but it's the same problem, right? And now if you just rearrange things just a little bit, sum n equals 1 to infinity, this right here is my a. And so I'm going to just move it to the front, right? 1/2 to the first power is just a half, times, then I have 1/2 to the n minus 1. Right? Do you all see that? And so this, well, let me do it this way. So this, in this, now looking at that, I can say it's a geometric series, right? It's geometric series. I have A is what? 1/2, that number in the front, 1/2, and R is just the number down there, 1/2 as well, right? Look at this formula. A is the number in front, R is the number being raised to the n minus 1. So the number that I have being raised to the n minus 1 is 1/2. They're both 1/2 in this problem, right? You all with me? So I have a geometric series with those two values, and now the only thing I need to do is check for convergence or divergence. So look at your R. Is the absolute value of R less than 1? Yes. Yes. Therefore, we're going to converge, right? So I'm going to put here, therefore, I'm running out of room, so I'm going to come back over here. So I'm going to put here, therefore, this series converges, right? It converges. Not only do I know that it converges, I know what it converges to, right? And so this series, I'll say therefore again, therefore, this series equals A over 1 minus R, right? A over 1 minus R. What's A?
1/2.
Over 1 minus, what's R? 1/2. Okay, that's 1/2 on top over 1 minus 1/2 is 1/2. And 1/2 over 1/2 is 1. And isn't that what was happening with those rectangles? We were saying as you add them up forever, it heads to 1. Questions? Let's do another one. Does this converge or diverge? 1/3 minus 1/9 plus 1/27 minus 1 over 81 plus dot, dot, dot. Yeah. Okay, this problem right here, we're jumping right into the frying pan here. I'm giving you a series, right? A series is a bunch of things being added up, isn't it? Yes? Bunch of things being added up? Well, this is a bunch of things being added up. Well, it's actually, adding and subtracting, right? But it's an infinite thing being added up, right? So the question becomes, first, can you rewrite this in sigma notation? So this goes back to the homework I gave you, those 5 problems, right? And ask you to find formulas for them. I want us to think about what the sequence is that we're adding up. See, you have to see that we're taking this sequence and adding them all up, right? So can you generate that sequence with a formula for me? So you have to realize that it's alternating, right? First it's alternating. So it's, you have -1. What power do I use if I want to start at a positive? N plus 1, N plus 3, right? N plus 1, that'll work. That'll get me alternating starting with a positive. And then all the numerators are 1s, right? All of these are 1s, so I have 1s on top. On the bottom I have what? 3 to the n. See, I gave you that homework problems. I gave you those homework problems because I really wanted you to have to work mentally to figure out formulas for exactly this reason, that when we got to this, you wouldn't be completely lost, right? You all comfortable with that? That goes here, right? That goes here. -1 to the n plus 1. I actually don't need the 1 on top, do I? Next to it. So I'll just put that over 3 to the n. So if you started plugging in numbers, right? Let's just check that this works. If you plug in 1 for n, you get 1 plus 1, that's 2. -1 squared would be a positive 1. And then n to the first power would be 3. So you get 1/3. Then you say plus. Now you let n be 2. So if you put 2 here, 2 plus 1 is 3. -1 cubed is a negative number. And then you'll have n squared. So that would give you -1/9. Make sense? Plus, minus, plus, minus. All right, nth term test. If we tried the nth term test right now, I'm not going to write it down, but if we did, take the limit as n goes to infinity of that.
0.
You're going to go to 0, right? Because the top here just switches back and forth between -1 and 1, so it's bounded, and the bottom gets infinite. So bounded over infinity goes to 0. What does that tell you? Nothing, right? So the nth term test would fail here, which means the only other thing we know is geometric. So is this geometric? Does it look like sum n equals 1 to infinity of a times r to the n minus 1? Does it look like this? Or if it doesn't, can you make it look like this? Hey, do y'all remember in class when I said when we wanted to do alternating, if we wanted to start positive, we just had to do n plus an odd number, right? An odd number? Could I go plus -1? Is that too much? Am I pushing too hard here? Is that not the same? If I do -1 to the n plus 1 versus -1 to the n minus 1, does it change what happens? Plug 1 in. What happens when you plug in 1 here?
2.
You get 2, so you get a 1 to come out, right? Plug in 2 here. What do you get? 3, -1 cubed is a negative, right? And so this is, we already know this is going to switch back, right? Positive, negative, positive, negative, +1, -1, +1, -1. Here, what happens when you plug in 1?
0.
You get 0. What's -1 to the 0? 1. Now plug in 2. 1, -1 to the 1 is -1. So you get 1, -1, then 1, -1, 1, -1. I guess what I'm trying to get you to see is this, that that's the same as adding -1, isn't it? And that's an odd number. I told you in class that if you want to start your alternating series and you want it to go positive, negative, you'll do n plus an odd number. If you want to do a series that goes, or a sequence that goes -1, +1, -1, +1, you do n plus an odd number. Even number, right? So do y'all see why it might be convenient for us to use n minus 1 here? Because then I could just be right there, right? Okay, but too many of you threw up in your mouth when you saw that. So I'm going to go back here, and I'm going to just leave it as +1, all right? And what I'm going to do is force an n minus 1. I'm going to force it. So I'm going to rewrite this. Kind of a gross idea, huh? Gross thought. All right, -1, -1. I'm going to go n, here we go. I'm going to force the -1. -1 plus 1, and then I already had a +1 up there, didn't I? Over, and on the bottom, I'm going to force it again, 3 to the n, and then I'm going to do -1 plus 1. All I'm trying to do is get everything that's to a power. I'm trying to get everything that's to a power to be an n minus 1 power so I can use this formula. All right, let's rewrite this. Sum n equals 1 to infinity. Oh, man. I can write that as negative 1 to the n minus 1 times negative 1 to what power? So I'm doing those two on there, right? Which leaves me these two, right? So negative 1 squared, right? Which is just 1. So it's going to go away, isn't it? Okay, over, this is 3 to the n minus 1 times 3 to what power? 1 power. Now this is sum n equals 1 to infinity. All right, that we said was 1, right? That's a 1. And this right here is a 3 on the bottom. That's 1/3. I'm going to put that out front. And then in here to the n minus 1, since these are both raised to the n minus 1, I can put this number over this number in the parentheses. So what goes in there? Negative 1/3. Did y'all see that? Questions on it? Is that geometric now? Does it look like a geometric series, the formula we have over here? Yeah? Okay, so this is geometric. We have A is a third, right? What's R? Negative a third, right? Negative a third. And when you take the absolute value of that, is it less than 1? Yes, so this is going to converge, isn't it? It's going to converge to what? So it converges to what? A, right? So 1/3 over 1 minus negative 1/3. Be careful because you have a negative, double negative there on the bottom. So 1/3 over 1 plus a third is 4/3. And then flip your fraction over. And what do you get? 1/4. If you take 1/3, subtract a 9th, add a 27th, subtract an 81st, and keep doing that forever and ever, you will converge to 1/4. Interesting, huh? Y'all hanging in there? All right, I'm going to do one more. I have 10 minutes and see if I can crank this one out. This is just an interesting problem. It's tied to this. I really like asking problems like this one on a test. Rewrite this number. Rewrite as a fraction. I want us to take the decimal, or yeah, okay, I'll just do this. 0.341341341, repeat it. So look, y'all have heard of rational and irrational numbers, right? Irrational numbers are numbers like pi, e, square root of 2. And the property of an irrational number is that when you write their decimal out, it never stops and there's no pattern. If you write a decimal for a number out, if it ever stops or if it ever repeats, it's called rational. This repeats, right? This is a rational number, which means there is a fraction that would create this number. Something divided by something will create this number. If I put pi up there, right? Pi, 3.1415, right? There's no fraction that creates pi. There's no number, integer, that you can divide by another integer to create pi. That's not possible. But if this stops or if it repeats, there's guaranteed a fraction that represents it. And I want us to find it. Now, on most calculators, there's a key for this to go from decimal to fraction, right? But the problem is, how are you going to type that in? Because it goes forever. You're not going to be able to type that in, right? So, somehow this is tied into geometric series, and I have 8 minutes. You ready? Watch what I do. Tell me if you agree with this. This is equal to, well, let's see what repeats. 341, right? 341, 341. Think about the position when you look at decimals. The first decimal is the tenths, then hundredths, then thousandths, right? So I could look at this as being 0.341 plus 0.000341 plus 0.000000341 plus 0.00000000341, and then that just keeps going, right? It's like if I put these two together, I get the first two groups, right? I put these together, I get the first three groups. Put them all, you see, this is me just writing it a different way. But this means 341 over 1,000, right? Tenths, hundredths, thousandths. So that's 341 over 1,000, right? This one would be 341 over what? Tenths, hundredths, thousandths, 10,000s, 100,000s, millions, right? So that's 1, 2, 3, 4, 5, 6. So look, this was a 1 with 3 zeros. This is a 1 with 6 zeros. The next one should be 341 over a 1 with 9 zeros, right? Yeah? And I could keep going, right? Somehow this is geometric. This is 341 over 10 to the third power plus 341 over 10 to the sixth power plus 341 over 10 to the ninth power plus so on and so forth, right? Now we're getting somewhere. Because these all look like I could create a formula to create this, right? Can you come up with the formula that would generate those numbers? I'm going to write it as a sum. Sum n equals 1 to infinity. Okay, what never changes? And all those numbers, 341 on top. That stays the same, 341 over. Now, the power here, we're going to have 10 to a power. And what are my powers? 3, 6, 9. Those aren't powers of 3, right? What are those? Multiples of 3. So how do you make a list that would jump 3 each time, starting at 3, 10 to the 3n? 10 to the 3n, right? That's our formula. We just have to make it look like this now. Now, the problem I have right now is that this is 3n, and we need n over here, right? So watch my first move. 341 over, I'm going to write that as 10 cubed to the n, right? That's the same thing? 10 cubed is 1,000. I'm going to keep that on the, what do I want to get rid of here? Yeah, I'll get rid of this. We don't need this anymore. By the way, the geometric series is on your tests sheet. It's the second one there. You see it right there? It even says geometric series, right? And see the formula, a over 1 minus r? It's right there for you. Everything's right there. You can use that sheet on your exam. You're welcome. I didn't get to on my Cal 2 exam. I had to memorize all of them. So, all right. So this is now sum n equals 1 to infinity. All right, check this out. 341 times, this is kind of a pretty, I don't know if this is a big leap, but you just tell me if you agree with this or not. Is that the same thing? So I rewrote this on the bottom here as 341 over 1,000. That's 10 cubed to the n, right? And then I split it into 2. 341 times 1 over 1,000 to the n. But then I said, wait a minute, it doesn't matter if this 1, I could look at that 1 as being 1 to the n as well, and then just put them together into a single fraction, like this. Trying to like force my r to be here. Do y'all see it? What, no questions? Now, am I ready? I'm at the form that I need or no? I need a -1. Okay, so I do -1 plus 1. And then that allows me to do this. Sum n equals 1 to infinity, and then 341 times 1 over 1,000 to the n minus 1 times what?
341 over 1,000.
Just, yeah, okay, I'm leaving that out there though. So this right here would just be 1 over 1,000, right?
Yeah.
To the first power. I don't need the power there, but just to show you that that's split up into 2 pieces. And now what I can do is take this 1 over 1,000, put it right here with the 341. 341 over 1,000, 1 over 1,000 to the n minus 1. Are we there? This is geometric. A, R, right? A and R. So we have a geometric A is 341 over 1,000. R is 1 over 1,000. And the absolute value of R is definitely less than 1, right? So this will converge. To A, 341 over 1,000 over 1 minus 1 over 1,000, right?
Comes out to 341 over 1,000.
Yeah, 341 over 999. Let's do this. When you get a common denominator there, you go 999 over 1,000. Because this becomes 1,000 over 1,000, you subtract 1 over 1,000, that's 999 over 1,000. And then when you do the flipping and stuff, you get 341 over 999. And I'd like for you now to type that into your calculator. Ooh. That's, and you get 0.341341,341?
Yeah.
Okay.
The little, like, converted to decimal.
Yeah. So there's an interesting property. I know it's time to go, but we are not done with this section. I'm going to send you an email after class, and I'll let you all know what homework to do out of this section, because we have not done quite a bit. All right, so there's this cool property that if you have something like 0.19